So the first three of them are kind of just, well, just say weird, but we're trying to learn something with those, all right? So the first question, number one, on the sodium citrate dihydrate, all right, is about freezing point depression. And where does it come from? I will give you the freezing point depression in these questions, but where does it come from? And let me make sure I got my little red finger thing to work here. Oh, no, not that. We'll get there. So, pen. All right, so we're going to try to calculate freezing point depression. I would highly recommend, if you're not familiar with colligative properties and some of these terms that we're going to go through, that the pre-lab reading for this chapter 11 would be very helpful, because I go through a lot more detail in that video than I have now. So let's just start with this. We said we're getting into chemistry. So it's a sodium citrate dihydrate. So sodium citrate dihydrate, okay? When we look at some of these things, when there is water molecules in the actual chemical that you then dissolve or put into solution, the water tends to go away. So in the end, when we count particles here in a little bit, we are looking only at the physical chemicals that we put into there. The water is part of the solution, so it disappears. So we have sodium and we have citrate. And let me ask you now, and this needs to come back a little bit, what is the valence, the charge on citrate? Is it positive or negative? Is it an anion or a cation? It's an anion. It's the negative because the cation is the what? The sodium. And knowing that sodium is 3 and there is nothing on the citrate, hopefully we'll remember the main cations of sodium and potassium have a valence of what? Positive 1, right? So that's why it takes 3 sodiums to equal the negative 3 on the anion for the citrate. Does some of this come back in a painful way that you thought would never come back to, all right? So I'm just trying to show you, some of this becomes important, certainly as we move on. So, but not for now. So this question, these are simple little questions, but it has to do with this. If we had 100 molecules of the sodium citrate dihydrate, okay, all right, if 80% of those molecules actually dissociate into solution, meaning they split apart, they separate. And again, not all chemicals dissociate at 100%. Sometimes they stick together, they form little clumps and they don't dissociate. So again, if this chemical dissociates at 80%, okay, if we had 100 molecules, how many would dissociate? Okay. Not hard, not a super math thing. If we have 100 and 80% dissociate, then we'd have 100 molecules total. We're saying 80 molecules dissociate on top out of 100 molecules total, all right? So obviously then when you get 80 molecules that dissociate out of the 100, 80%, 80 out of 100 dissociate. I know, it seems stupid. We're getting to a point here. If I have 100 molecules at 80% dissociation, 80% dissociate, but that also means then what? How many molecules do not dissociate? Because what we're going to do here in a minute, what the whole point of this is to count molecules, count particles, all right? So we need to count things. In this case, since we had 80% or 80 out of 100 dissociate, that means there are 20 particles that do not dissociate out of that 100. I can count them. There will be 20 particles because they will not separate. They stay glued together. They can count them as individual particles. The problem comes with the 80 molecules that dissociate because I won't end up with 80. Would you agree? If I start with 80 and they dissociate, they separate, how many particles will I get from the 80 dissociated molecules? Well, it depends on the formula. How many particles are in the formula? How many sodiums? 3. How many citrates? 4. So I don't care what the particles are, but there would be 4 particles for every molecule that dissociates. That's why if we have 80 molecules dissociating, they're going to dissociate into 4 particles from each of those. So the total number of particles, once those all separate into solution, would be 320 particles. And those are the particles coming just from the dissociated molecules. All right? So then if the question is how many particles total will you have floating around in this solution when you start with 100 molecules, well, you get the 20 particles from the undissociated and the 320 particles from the dissociated molecules gives you a total of 340 things floating around. And the whole point of knowing this is that if we look at the freezing point of water, water freezes in terms of degrees Celsius. What does water freeze at? What temperature does water freeze in Celsius? 0, right? However, how come then the ocean isn't frozen? How can you be below 0 degrees Celsius in the ocean and it's still water? Because the more stuff floating around in the water, the lower it takes to freeze the water, because those molecules interact with the water molecules and keep them from freezing. So would you agree here, the more particles we have here, the lower the freezing point of the solution. In fact, you can actually determine how many particles are in solution by how it changes the freezing point of water. And that's the basis of how we can use the freezing point to make our isotonic solutions that we're going to talk about in a minute. All right. So point to this is now in this example, we've counted the total number of particles. The whole point of this is that we calculate an I value. And an I value is simply the number of particles that you generate, that is 340, out of how many molecules did you start with? In this case, we started with 100 molecules. So we got 340 molecules out of 100, okay, molecules, 340 particles, if you will, out of 100 molecules. Divide that out, we get 3.4. So this I value, this constant we have for this chemical, sodium citrate dihydrate, it has an I value of 3.4. And then the reason we're leading up to this is the formula for the freezing point depression is a negative 1.86 degrees Celsius for every value of I. Okay, so since our I value is 3.4, we take 3.4 times the negative 1.86 and we see a negative 6.32 degrees Celsius. So instead of freezing at 0 degrees Celsius, because of the number of molecules we have in that solution, it would take a lower than 0 value, a negative 6.32 degrees Celsius before that solution would freeze due to the interaction with the number of molecules that we have in the solution. Okay? So you can use, the take-home message here is you can use a freezing point depression as a measure of how many particles are in the solution. Okay? We are then, and half of the questions we do for isotonicity are based off of freezing point depression. The other half are based off of what we call sodium chloride equivalence. That is finding an equivalent amount of sodium chloride that this chemical mimics, all right? So let's start with this here a little bit. And in these questions, the tetrahydrolysine, okay, I give you both a molecular weight and its I value. Remember the I value we just calculated? I gave it that value already for this drug, so we don't have to calculate it. I already know it, so it's an I of 1.8. What we're going to try to do, and this becomes important, I'm always going to give you an E value. I will rarely make you calculate it, but this is where it comes from, even if I never mention this again. An E value stands for the sodium chloride equivalent value, and it takes the molecular weight of sodium chloride divided by the I value for sodium chloride. So the I value, like we just did, for sodium chloride is 1.8. Okay? What you do to determine then the sodium chloride equivalent for any other chemical in relation to sodium chloride is to take its I value and multiply by a ratio of the I value over that chemical's molecular weight. Okay? So in this case, we're going to if I just set this up for the tetrahydrolysine, we realize its I value is the 1.8, its molecular weight is 237. So if we take the 58.5 divided by the 1.8 times the 1.8 divided by 237, if we do that math, we get 0.25. Okay, where did Wichita go? Are they turned off their own camera? Are you guys still there in Wichita? Can somebody? Okay, yay. All right. So, sorry, I'm just looking at my screens up there. You're thinking, okay, this seems so lame. But anyway, so I give you an E value of 0.25. What does that mean? This is super important that you understand. An E value, when you have it, represents the weight of sodium chloride in grams per gram of the drug. And in this case, our drug is tetrahydrolysine. So when I say the E value, by doing this math for tetrahydrolysine is 0.25, we can now convert between sodium chloride weight and tetrahydrolysine weight, because I know 0.25 grams of sodium chloride is equivalent to 1 gram of tetrahydrolysine, okay? In terms of its osmotic properties, in terms of its effect on the freezing point depression, okay? So when we're talking about its effects on isotonicity or tonicity, this is how much we can relate of sodium chloride to the drug we're interested, tetrahydrolysine, okay? All I want you to realize here is that if it's 0.25 grams of sodium chloride per gram of drug, that is the same as 0.25 milligrams of sodium chloride for 1 milligram of the drug. Would you agree? Whether it's grams over grams or milligrams over milligrams, you can use the same number. And you'll see it's sometimes easier to use this in milligrams than it is in grams. Okay? Let's keep going because the background becomes less important. Now, here are some typical calculations that you're going to have to do once you know the E values and once I give you the freezing point depression values. So in this question, so this is one I'll let you work on. It says, how many milliliters of tetrahydrolysine hydrochloride are contained in a half-ounce bottle? And I didn't give you this. I don't think I'm thinking 1 ounce, 1 fluid ounce is 30 milliliters. I'm sorry I didn't give you that on the question. So don't make this hard. This is kind of a straightforward one. But if 1 fluid ounce is 30 milliliters, if we start with a half an ounce, how many milligrams of tetrahydrolysine are in a 0.05% solution? Okay, that's very similar to what we've already done. You'll see why we need to know this first. I'm going to have a half-ounce solution. Okay, it's going to contain 0.05% weight per volume of tetrahydrolysine, so I need to know the weight of my tetrahydrolysine in that solution. Step one, do you get or are you getting 7.5 milligrams? And again, that's from a half ounce times 30, which would give us 15 milliliters. 15 milliliters times 0.05 grams per 100 milliliters gives me my weight in grams. And then if I multiply that by 1,000, that would give me milligrams at 7.5 milligrams, all right? So here's the deal. That's the therapeutic concentration I need for my tetrahydrolysine in my eye drop, okay? I have 15 mils of an eye drop, so I need to have 7.5 milligrams of tetrahydrolysine. The problem here is I need to know its effect on tonicity because, again, I didn't go through this deal. Can you just put water in your eye for an eye drop? Or can you just inject water into your blood? Let's use blood as a better example. Why? Because it would cause what? The blood cells to shrink or to swell? To swell up because fluid goes to try to equalize pressure caused by the dissolved particles. So again, we need to instill fluid into our veins that have the same osmotic pressure in terms of whatever is the particles dissolved in it, that equals blood, okay? And if it's equal, then we call it isotonic. Isotonic means the same osmotic pressure or the same tonicity as blood or biologic fluids. A lot of what we're going to do here in Chapter 11 really talks about eye drops and formulating eye drops. Eye drops also need to be isotonic because if you have them too hypertonic or too hypotonic, then they cause irritation and problems in the eye. So again, we're still striving for isotonic. So I guess my question here is, if I have 7.5 milligrams of my tetrahydrolysine in 15 milliliters, is that isotonic or hypertonic or hypotonic? That's what we're solving for, okay? So I know there's 7.5 milligrams of tetrahydrolysine. So now that we know the E value that we already calculated, remember it was 0.25. The E value for tetrahydrolysine we now know is 0.25. So answer me this. How many milligrams of sodium chloride would be equivalent osmotically to the amount, my 7.5 milligrams of tetrahydrolysine? Because I know that's the amount of tetrahydrolysine I need, 7.5 milligrams, therapeutically, but I want to know how much sodium chloride that mimics in solution. Because I know how much sodium chloride it takes to be isotonic. We'll talk about that here in a second. But now, try to use the E value. So I'll just set this one up. Well, and again, let's just look down here because this is setting it up in milligrams, which is obviously the easiest. We said to make my 0.05% solution, I need 7.5 milligrams of tetrahydrolysine. Remember the E value of 0.25 means 0.25 milligrams of what? Sodium chloride. The number goes with the sodium chloride. This is the most important thing I can emphasize at this point. An E value, the number goes with sodium chloride, and it's per, in this case, milligram of drug. So I know it's 0.25 milligrams of sodium chloride per milligram of tetrahydrolysine. So if I multiply that way, milligrams of tetrahydrolysine cancel, and 0.75 or 7.5 times 0.25 gives me 1.88, and clearly the milligrams of sodium chloride. Now, here's what's important. Did I just say that there are 1.88 milligrams of sodium chloride in tetrahydrolysine? No. This is how much sodium chloride the tetrahydrolysine mimics. That is, if I put 7.5 milligrams of tetrahydrolysine in water, it produces the same osmotic force as if I had 1.88 milligrams of sodium chloride. Is that clear? We're showing how much sodium chloride is mimicked by that amount of tetrahydrolysine. And the reason we want to know that is this. How many milligrams of sodium chloride would it take to make that half-ounce bottle isotonic? Because here's what we know about sodium chloride. What is an isotonic concentration of sodium chloride solution? And this is a memorization thing. You have to memorize this for this chapter. And for this whole thing, you got to know 0.9% weight per volume. What does 0.9% mean? 0.9 grams of sodium chloride per 100 milliliters. That's just your normal weight per volume. Use that information and tell me if I'm starting with a half fluid ounce, how much weight of sodium chloride in milligrams would I need to make it isotonic? Okay, because you've got this percent right here, we've got this volume right here, and remember to give me my final weight in milligrams. Go to it. Start with this and convert that using that into a weight, and then remember, go from grams to milligrams. Do you remember we said a half ounce times 30 mils per ounce would give us 15 milliliters? 15 milliliters times 0.9 grams over 100 milliliters would convert that volume of isotonic sodium chloride to the weight of sodium chloride it would take to provide that. But that weight is in grams, so if we multiply by 1,000, we can convert that number from grams to milligrams, and we see it's 135 milligrams. All that says is if I put 135 milligrams of sodium chloride in 15 milliliters of water, what would the concentration of sodium chloride be? 0.9%. That would be isotonic. So this is the weight of sodium chloride for that volume I need to make it isotonic. So let me ask you, is my tetrahydrolysine, therefore, if I don't put any extra sodium chloride in there, if I just put my 7.5 milligrams of tetrahydrolysine in there, is that isotonic? The answer is no, because we said that 7.5 milligrams of tetrahydrolysine was equivalent to how much sodium chloride? 1.88. Do you remember we solved for that? We just solved and said that that same volume would require 135 milligrams to be isotonic. Since this number is below that value, we have less sodium chloride, which means our solution would be hypotonic. We wouldn't have as many particles as we need to make it isotonic. Okay? All right. Throw that away. This becomes now more important. Okay, and hopefully we're getting closer to what we all eventually need to do for the exams and so forth. All right, so in this case, I want you to calculate the concentration of the sodium bisulfate or glycerin that are isotonic with body fluids. Okay, and we're going to do this in two steps. Let's start with the sodium bisulfate using this value right here, and this is most important. This is the values I'll give you on the exam. A delta TF 1%. And I'll get to what that means here in a second. So my first question to this, and this is what you have to memorize. This is a memorization point. What is the freezing point of an isotonic solution? Remember how we said water freezes at 0, but your blood is not water. I don't care how ice cold you are, it's not water. You got stuff floating in there, so it doesn't freeze at 0. What does it freeze at? This is memorization. Remember, it freezes at less than 0, so that's why the negative sign, where all these values will be less than 0. We're talking about freezing point depressions, less than 0. Blood freezes at negative 0.52. So you have to know this. I will not give this to you on the test, and if you don't know that value, you cannot solve these questions. It is key. Okay, so you must remember, memorize 0.52 degrees. Negative 0.52 degree is the freezing point of an isotonic solution. Okay, now You're going to see why we need to use that information. This question says, what is the freezing point depression of a 1% concentration of the sodium bisulfate if I give you this value? This is a stupid question, but it tells you, what does this mean? What does delta stand for? Delta, delta, delta. Change in capital T temperature. So what is the change in temperature? Freezing temperature. So the little f stands for freezing. So what is the change in the freezing point of a 1% solution? And these values I give you will always be standardized for 1%. Okay, so that little 1% allows you to know this is the concentration. 1% of this drug produces this decrease or this freezing point depression. Okay, and so a delta TF 1% means that 1% concentration reduces the freezing point by that amount. So in my question here saying, well, if I have a 1% concentration of sodium bisulfate, I realize that that would produce a negative 0.36 degrees Celsius reduction. So let me ask you, is a 1% concentration of sodium bisulfate isotonic? No, what did we just say a freezing point depression of an isotonic solution would be? Negative 0.52. If this was negative 0.52, it would have been isotonic, but it's not. All right, so now the question will be, how can I determine how much sodium bisulfite I need to make an isotonic solution? Well, it's simply setting up this proportion. So this is really the take-home message. You must be able to do this. If I give you a delta TF value, 1%, and it will always be 1%, set up the proportion of the degrees on top over the 1% in the denominator. And that will convert the freezing point temperature to the concentration of the drug. For this concentration of drug, 1%, you lower the freezing point 0.36 degrees. Now we can set that equal to, in this case, I don't know how much drug I need, but I know what it needs to freeze at. It needs to freeze at a negative 0.52 degrees Celsius. That's an isotonic solution, freezing point. So if I set it equal to 0.52 degrees Celsius over X, solve for X, and I am solving for the percent concentration, because remember this value here is percent. The percent concentration that would produce a 0.52 degree reduction in freezing point. And for this drug, it's 1.44%. How are we doing? I would just say, I know there's a lot of background in some of the previous questions, but this into this is absolutely essential. And then knowing I have degrees Celsius in the numerator, I have percent concentration of the drug in the denominator, I can set that equal to and solve for any one of those other two, depending on the situation. All right? All right, let's change gears now. You said freezing point depression. The other way of calculating isotonicity is using sodium chloride equivalence method. So we've already mentioned this, but what is the concentration, an isotonic concentration of a sodium chloride solution? 0.9%. So we've mentioned that, but that's the other memorization thing. So again, if I walk up to you on the street, I'm going to ask you, what does a freezing point of an isotonic solution? Negative 0.52 degrees Celsius, Dr. David. What is a sodium chloride isotonic concentration? 0.9%. If you can, again, truly, those are only the things you have to memorize. I will give you everything else you need to solve these questions, but that's what you need to know. Okay, let's beat that to death. So now my question is, in my glycerin example here, how many grams of sodium chloride, well, not quite yet for the glycerin, but how many grams of sodium chloride does it take to make 0.9%? So this is kind of a stupid question, but that's obvious that if it's 0.9%, 0.9 grams per 100 mils, if we're starting with 100 mils, that means we would need 0.9 grams. Okay, we'll come back to this. You'll see why we need to know this here in a minute. But now let's ask you this. How many grams of sodium chloride is 1 gram of glycerin equivalent to? So if I have 1 gram of glycerin, how much sodium chloride does that mimic osmotically? Well, that's the definition of the E value. Remember, if I give you an E value, you know that it is 0.35 grams of what? The number, the 0.35 goes with what? Sodium chloride. So it's 0.35 grams of sodium chloride per gram of the drug. In this case, per gram of glycerin. Do you see where this is a ratio of sodium chloride to drug? You must be able to take your E value, set up that proportion, or that ratio I should say, so you could say, all right, I need 0.35 grams, I get 0.35 grams of sodium chloride equivalents for every gram of glycerin. Okay? Because now, the whole point of leading up to this is if I want to make a solution isotonic with glycerin, if I'm going to make 100 mils, how much glycerin do I need to make it isotonic? Well, I know that it takes 0.9 grams of sodium chloride. Do you remember that? That's how much grams of sodium chloride it takes to make 100 mils isotonic. So why don't we just convert that weight of sodium chloride to an equivalent weight of glycerin? And I can do that because I have this E value. But remember now the 0.35 goes in the denominator because I have grams of sodium chloride in the denominator. So when I multiply basically 0.9 grams by 1 gram divided by 0.35, if I divide by 0.35, I cancel sodium chloride and I get glycerin. So 0.9 divided by 0.35 converts to 2.57 and that becomes grams of glycerin. You see where the E value can convert grams of sodium chloride to grams of drug, or grams of drug to a grams of equivalent amount of sodium chloride. That's why the E value is very important, but you must be able to set up the proportion with these units correctly. That's where it goes wrong the most often. So, since it was 2.57 grams per 100 mils, that's the 2.57% of glycerin. Do you see where we're able to use the E value to come up with isotonic glycerin, and we were able to use the delta TF to come up with an isotonic sodium bisulfate? All right. This is starting on question 4. These are quiz and exam level questions. Everything we've done up to this point has been foundational. We'll see how you can apply it now in these questions. These are the kind of questions you're going to have to answer on the quizzes and the exams. So we have a prescription here. So let's read and interpret our prescription on the left-hand side. It says we need sodium sulfacetamide at 2.5%. The therapeutic concentration of the drug we need in our eye drop is 2.5%. Okay? It then says sodium chloride QS. So it just says add whatever amount of sodium chloride you need to the sodium sulfacetamide to do what? What do you think the sodium chloride is being used for? A tonicity adjuster. We will add whatever amount of sodium chloride we need to make sure that our final product is isotonic. So we have our active drug, sulfacetamide, we have our tonicity adjuster, sodium chloride. And we see the percents that are needed for that. We're going to make a total volume of 45 milliliters. Okay? So you're going to need to know how much sodium sulfacetamide, God Lord, sodium chloride, we need the weights of those amounts of things so that when combined we have a 45 milliliter, that's 2.5% active ingredient and isotonic. So the first step here, what is the freezing point depression caused by the sulfacetamide? So if I give you the delta TF for sulfacetamide at 0.14, my question to you is, given the therapeutic concentration we are going to use, and what is that? Where do I find that? On the prescription. What does the prescription call for? 2.5%. So if I'm going to have 2.5% of that drug in my solution, what percent or what decrease in freezing point will that cause? All right? So I'll work through this one. I'll show you that work. All you need to do is, can you do this? This is the first step. And we'll practice writing that down. 0.14 means 0.14 means 0.14 degrees Celsius over a 1% concentration. Remember, it'll always be over 1% from the delta TF 1%. Now, some of you are going to say, Dr. David, you're being lazy. There's no negative signs there. Didn't we say that all of these temperatures are freezing point depressions? They're all going below 0. And the answer is yes. So these answers are all, these numbers reflect negative values. However, if you leave the negatives in there, you're going to mess yourself up. So you're going to see me do all of my work without negatives. And trust me, your math will work out better. So you'll see that in here in a minute. If you want to treat it and be a purist, put a negative and sign in front of that, please do. But you'll see the negatives always cancel out and it doesn't change the math at all. So you'll be more successful, I think, if you just ignore the negative signs. And just know that when I say the word depression, it means negative value, okay? So, is everyone okay where we're at so far? We just pulled this number down to there and set it up. We then take the concentration and we put it in the denominator here. And so if I can solve for x now, x represents how many degrees depression would be caused with a 2.5% concentration if I know 0.14 degrees are depressed by a 1% solution. So we're just setting up a proportion. So does everyone see where the math comes out to be 0.35 degrees Celsius? And again, it's inherently a negative value, okay? But it's 0.35 degrees. Is that isotonic? That's kind of the next question, because we said a freezing point depression of isotonic is 0.52. So how much do we still need to get? If this is our target, and the only active ingredient we have is our sulfacetamide at 2.5%, then we need more. We don't have enough, because this drug gives us that value. So the difference between the two is the amount of freezing point depression that I still need to get. Okay? And this is where you could take a negative 0.52 and subtract a negative 0.35. And what value do you get when you're done? A negative 0.17. Do you see where the negatives cancel and you end up adding to a negative value? And so if you love negatives in math, keep them, all right? But if you just want to get the number right, I suggest just ignore the negative signs for all of these calculations, and they will work out fine, all right? But what we still need then is 0.17. How are we going to get it? Who are we going to call? Not Ghostbusters. We're calling sodium chloride to the rescue. We can use sodium chloride to get us the rest of the freezing point depression we still need. So the question then is, what concentration of sodium chloride would I need to get the amount of freezing point depression I still need to get? Well, let's take the delta TF value rather for sodium chloride, which is 0.58 degrees Celsius for every 1% concentration. Now I know the amount of freezing point I need. That's what came from the previous question. When we took 0.52 minus what we got from our drug, we still need 0.17, so that's the amount of freezing point depression I need just for my sodium chloride. So if I put that over X, I'm solving for the percent concentration of sodium chloride, which would give me a 0.17 degree depression in my freezing point. So when I cross multiply and do my math there, take 0.17 divided by 0.58, I see that what I need is a 0.29%. And don't forget the units come from the percent here. So the final units there will be percent, 0.29% sodium chloride. So does that tell us how much sodium chloride we need? Not yet. We're one step away. Would you agree? I know my concentration. Do I know the volume that I'm making? 45 mils. So do you see where our next step is to combine those two? So to determine the actual grams of sodium chloride needed to make this solution isotonic, I have to factor in the volume I'm making times my concentration. And this is why that whole chapter 6 was important. When I say 0.29%, that's 0.29% weight per volume, that's 0.29 grams of sodium chloride per 100 mils. That's the concentration we just calculated. So if I multiply that by 45 mils, mils cancel, and I solve for the weight of sodium chloride. This is kind of cool. Would you agree? I know that if I take and dissolve 0.13 grams of sodium chloride, or I weigh that amount, and I weigh it with my required amount of sodium chloride, or sulfacetamide, I'm sorry, I'm making this bad. The weight of the sodium chloride, 0.13 grams, with the weight of the sulfacetamide combined together and dissolved in a total of 45 milliliters produces an isotonic solution that has the therapeutic concentration of sulfacetamide I need of 2.5%. Okay? You see where we use this. Again, I'll still back up and just say, okay, this is the big part of what we're trying to do here is being able to take the delta TF 1%, set them up as a proportion here or as a ratio so that we can solve. All right. Now, let's do the same thing, but using the sodium chloride equivalent method. But we're still trying to do the same thing. We're going to have an active drug, okay? In this case, the dimethylbarium bromide. That's our active drug at the concentration we need therapeutically. So that's how much drug we have to have in our I solution. But that may not be isotonic. So let's use our essentially preservative chlorbutanol as our tonicity adjuster and add whatever amount we need so that we make an isotonic solution with a final volume of 60 milliliters. Is it clear what we do? We have one active ingredient, one tonicity adjuster that's added to the extent we need to make an isotonic solution such that we have a final volume of 60 milliliters. Isn't that what we just did in the previous question? But we used the freezing point depression method to calculate it. Same thing here, but now sodium chloride. So unfortunately, the methods of getting to where you need to go are different. So in this case, the first thing you actually now need to know that we didn't do with the sulfacetamide is the actual weight of your active ingredient. How many grams, I'll give you a second to do this. I'm looking at the time here. I've got a little bit of time. How many grams of the dimercurium bromide do I need to make this volume have that concentration? 60 milliliters of solution. Take the concentration therapeutically that we want, which is 0.25 grams of the drug for every 100 mils. I multiply that over, and I know that when I make this, I'm going to have to use 0.15 grams of the dimercurium bromide. Everyone okay with that? It's a little different than what we did in the previous thing, but now I know for my active ingredient, I know its weight in grams. Because what I'm going to do is convert that weight in grams of drug to the weight in grams of sodium chloride that is equivalent osmotically to the drug. Okay, I'm going to convert weight of drug to weight of sodium chloride. How in the world can I do that? What could I use? My E value. I would argue you're starting with a 0.15 grams of drug, and an E value of 0.12 means what? 0.12 grams of sodium chloride. The sodium chloride goes with the number 0.12 grams of sodium chloride per gram of drug. And since I want to go from drug to sodium chloride, I'm going to multiply by that so that grams of drug cancel. And when I multiply 0.15 by 0.12, I see that I get 0.018 grams of sodium chloride. And again, that's not how much sodium chloride is in the drug, but if you put that drug, that 0.15 grams in solution, osmotically, it mimics as if you had 0.018 grams of sodium chloride. So that's how much sodium chloride tonicity is equivalent to the amount of drug that you need. This now I can deal with because do I know what it takes to be osmotic using sodium chloride? What concentration do I need to be osmotic sodium chloride? 0.9%, right? 0.9%. So now you'll see my question here is don't worry about the drug thing here yet. Simply answer me this. How many grams of sodium chloride would it take to make this volume isotonic? Doesn't have anything to do with the drug at this point. If I want to make 60 milliliters be isotonic with sodium chloride, knowing that an isotonic solution for sodium chloride is what concentration? 0.9% weight per volume. Simply tell me what amount of sodium chloride would I need? Did you get 0.54 grams? And that's taking 60 milliliters times 0.9 grams divided by 100, so the mils cancel, and that's the weight of sodium chloride it would take to make 60 milliliters be 0.9% weight per volume. Do we have that amount? What did we say we got from the drug? We said we got this really actually fairly small amount of sodium chloride equivalent from the drug, so we still need a lot more. So let's take this amount that we're getting from the drug and subtract it from the amount we need. So in this question here, in terms of how much additional sodium chloride do we need, if this is our target, 0.54, and this is what we get equivalent-wise from the drug we'll be dissolving, then what we still need to get from sodium chloride is 0.522 grams. That's the weight of sodium chloride I still need to add. And if we were using sodium chloride, we'd be done. Yay for us. But we're not. Would you agree? What are we using as our tonicity adjuster? Chlorobutanol. So I know the weight of sodium chloride I need, but I need to convert that to the weight of the chlorobutanol that would be equivalent to that amount of sodium chloride. So for the sake of time, I'll just keep going. This is what we just calculated we still need. We need the equivalent of 0.522 grams of sodium chloride. So let's figure out how much chlorobutanol it would take to be equivalent to that by using its E value. But remember, 0.24 means 0.24 grams of sodium chloride per gram of chlorobutanol. Since I want to convert to chlorobutanol, I'm going to put 1 gram of chlorobutanol in the numerator and 0.24 grams of sodium chloride in the denominator. So when I multiply it by 0.522, grams of sodium chloride cancel, and what I'm converting to is an equivalent weight of chlorobutanol. So it turns out I need to weigh 2.175 grams of chlorobutanol. Dissolve that in water, and that will be equivalent to having dissolved 0.522 grams of sodium chloride. So I will produce the same amount of osmotic force as that amount of sodium chloride. When mixed with my active ingredient, then I'll have an isotonic solution. All right? Last question, and the last question, and I'll just kind of work through this, you can kind of watch me at this point for the sake of time, is simply this, and you've noticed this, that the colligative properties are additive. That is, you can take the colligative properties of multiple drugs, add them all together, and they will have a combined effect. So in this case, we are going to combine two active ingredients, the binoxonate and the fluorescein, and add those together. And if there's still not enough to produce the total amount of tonicity we need, we will add boric acid as a tonicity adjuster. All right, so just kind of watch this in the set. So this are using the sodium chloride equivalent method. So in this case, I want to know how many grams of the drug. So the first drug, the binoxonate, how many grams of that do I need to be therapeutic? Knowing that I'm having that concentration and that volume, how much drug do I need? That's what will dictate that. So again, this volume times that concentration. So 45 times 0.4 divided by 100, so the mils cancel, say that for this prescription, I need 0.18 grams of binoxonate. But how much sodium chloride will that be equivalent to osmotically? Okay, so how do I figure that out? I take the grams of the binoxonate I need, I take its E value, and I set it up, and I'll multiply here so that I can convert from the grams of drug to the grams of sodium chloride that drug is equivalent to, and I found that I need to get 0.031 grams of sodium chloride equivalent from that amount of the binoxonate. Everyone all clear with that? That's what we just did in the previous question. Now we got to just remember this, so we'll come back to this number, but now we've got to move into the fluorescein. So let's talk about the fluorescein. If I'm going to make 45 milliliters, have this concentration, then of the fluorescein, I need to have 0.113 grams of fluorescein, okay? That's just the weight of the drug I'm going to be putting in the solution to have the right concentration of my drug. But what kind of osmotic forces will that amount of drug produce? How much sodium chloride will this be equivalent to? So let's solve for that. This is the amount I'm going to have. Here's my E value. I bring my E value down, and if I multiply that weight then by 0.31, grams of drug will cancel, and I'll have my equivalent grams of sodium chloride. So I now know the equivalent weight of sodium chloride for my two active ingredients. What I still don't know, though, is what is my target? How much sodium chloride equivalent do I need? This is always going to be done the same way, but it's going to start with the amount or the volume you're trying to prepare. In this case, it's 45 milliliters. This will always be the same. Is everyone clear on that? An isotonic sodium chloride concentration is 0.9%. So it's always going to be 0.9 grams over 100 mils times whatever volume you're trying to make. So for that volume, I'd need to have 0.405 grams of sodium chloride total. That's the total sodium chloride I would need to make 45 milliliters be isotonic. So now, if that's my total, let's subtract what I get from my binoxonate, subtract the total that I get from my fluorescein. But subtract what, though? Not the weights of the drug. Do you see where things could go bad here? I'm subtracting the equivalent weight of sodium chloride for each of those drugs, the things we calculate. That's what we subtract from our sodium chloride equivalent total. And what I still need to get is 0.339 grams. So I still need to get that amount of sodium chloride from what? From the boric acid. So that's what I'm going to have to use boric acid to provide. So if that's my target, that's the amount of sodium chloride I need from boric acid, then I'm going to take its E value. But remember, since we're converting from sodium chloride to a drug, we set it up for every 1 gram of boric acid, there's 0.52 grams of sodium chloride. So if I divide by that number, I have then finally converted to the weight of boric acid. So that grams of boric acid, 0.652, when added to the weight of my fluorescein and the weight of binoxonate, all of those things mixed together in a total volume of 45 mils would produce an isotonic solution. Because remember, those properties are just all additive.